Okay. Now, for set and drift. Remember, the way we're going to do this is not necessarily identical for how we're going to get into contact management with radar problems just yet. But I do want to do it just to just to kind of show you how the two concepts of set and drift and radar and relative motion are connected to one another. That way you can have that in the back of your mind when we go into contact management, to, I think, better make everything feel more concrete. So in the original problem I used 090, but I'm going to make it a little more interesting by taking a more not unusual, because none of the courses are unusual, but one that's not exactly due east or due west. So let's say we're going 130 at 15 knots, like in the original problem, and we are expecting a 30-minute DR. So from our 0800 fix to our 0830 DR. Now, it doesn't need to be labeled as a fix and a DR because we're not, this is not a chart. So this doesn't have to have a fix at the beginning and a DR position at the end. What it does need, though, is just a vector showing that direction. And I kind of gave the game away by erasing it to there. But we've got our direction here. And then if we wanted our distance along it, well, like I said, we're going in a 30 minutes of time, and we're at 15 knots. So, I mean, you know the answer is 7.5 miles that we're going to travel, but let's actually use the logarithmic scale so you can get used to that. Remember, if you're using the radar transfer plotting sheets, this is not the logarithmic scale you're going to be dealing with, and it's actually, this one's easier than that one, but I think this one's also more helpful in understanding what's going on. So in this case, we'll start at the speed scale. So we're going 15 knots here. So we're just going to put a little mark on the 15. And we are traveling for a total of 30 minutes here. So if we're going from 15 to 30, or we're going at 15 knots for 30 minutes, if you connect the two lines, the angle between them does not matter at all, but where they intersect the third line, right there, lands halfway between 7 and 8 in the nautical miles side, meaning you would go 7.5 nautical miles. If we wanted to do this differently, let's say if we sailed for 8 knots, or for 8 minutes, and went 3 nautical miles, well, you would mark 8 here and 3 here. You would connect the two together, like so, and you would get just over 22 nautical or 22 knots, 22 nautical miles an hour. So this scale, all you got to do is you mark 2 points and connect the dots and extend them to the third line. Find where they intersect the third line, whether it be this one, or this one, and that will give you the third value you're missing. And all of this is based on 60D Street. It's just a graphical representation of it, so you don't have to do the math in your head. Now, for 15 nautical mile, or 15 knots in 30 minutes, you don't need the scale for that. You know it's 7.5 nautical miles. However, if it's something more difficult, I mean, in the case of 8 minutes to go 3 miles, I wouldn't know what the answer off the top of my head is, but evidently it's like 22.5 knots. This will be a lot faster than actually having to take out your calculator and do the 60D Street problem. So we would be going 7.5 miles in our 30 minutes. So if we take out our dividers, or our compass if we wanted to be more realistic, but I need to find a lead before we can do that. And you measure halfway between 7 and 8 here, which is marked that little tick mark. By the way, also even smaller tick marks, that's tenths. So you can see there's 7 point, well, that's kind of in shadow, so you can see there's 3.1, 3.2, 3.3, 3.4, and then 3.5 right there. So we'll come out to 7.5. Mark it there. Find where it ends, which is also marked with that little thing there. And then if we wanted to, we could label this E and R, because this is our course and speed right here. Now let's say when 8:30 came around and we took our fix, let's say we ended up 2 nautical miles away from our fix in the direction of 280. So how we could do that, we would do our direction first. Right there. Slide it down. Draw that line out. Then we would measure out 2 nautical miles. Place it along it. Right there. So if this is where we were supposed to be going, and this is where we actually were, we already know that this right here is the direction of set and drift. We'll label that RM, because just like if you imagine this on a paper chart, this would be our DR position and this would be our fix. And we would see that we got pushed this far in this direction. And we know this is 280 because I gave you that, but we don't necessarily know the speed of the current. We know we went 2 nautical miles. However, that's not equivalent to our speed. We went 2 nautical miles over the course of 30 minutes. So what is the speed of the current there? Well, I know it's 4 knots, but let's try out the logarithmic scale. So if we took 30 minutes to sail 2 nautical miles, we connect the 2 lines together, and we get 4 knots. I was a little off, like it's a little bit before that, but we come out to 4 right there. So we know that our current has a drift of 4 knots. We also know what our course and speed made good are very easily. Our course made good is just, if we connect these dots here, .140. And our speed made good, well, first we have to measure how far we went. So we can measure this distance, take it over to our scale. It comes out to 6.8 nautical miles. So we went 6.8 nautical miles in 30 minutes. So we'll come to, we got 30 again, and then 6.8 is just about there. So this is when it gets a little ambiguous when you're using smaller fractions like that. However, it still should give us a pretty representative answer of about 14 knots. So we made good 14 knots on a course of 140 because a current of 280 at 4 knots pushed us right of track. This is what you do when you're on a paper chart and you're calculating set and drift. Now we're just doing it on a maneuvering board. And this maneuvering board, it just makes it a lot easier to work with. It makes it more obvious, and it doesn't clutter up your chart. So if you ask me, it's better to do set and drift problems on a maneuvering board if you're doing them manually at all. Now, if we wanted course to steer on a chart, we would just extend our set and drift vector the opposite direction and find and set the distance in the opposite direction. And find, it's right there, that course right there. However, if you know where I'm going from here, if we were to go on this vector this way, make this our ER, then the current would remain the same, and it would push us down to making good our original intention of 130 at 15 knots. But this vector is larger. And this is something that really got glazed over when we did set and drift in TNAV. That I think they did a disservice by not explaining this to you. But the only way for that to work is if you increased speed. You see, if this is moving 7.5 nautical miles in 30 minutes, to make this work, you would have to be going, let's see, 9.3 nautical miles in 30 minutes. So this is on course, looks like right about 123, 124. So let's just call it 124. It's kind of in between the two. But this is on course 124. If you wanted to make good 130 at 15 knots, you would have to change course to 124, but you would also have to increase your speed to fight the current. And I think that's something that that your teachers might not have touched on during TNAV. Now let's see exactly what you need to increase your speed to. I said 9.3 nautical miles. So if we do 9.3, right around there, in 30 minutes, that would require a speed, it's going to be 18.6, right? A speed of just between 18 and 19 knots, so 18.6. So if you wanted to have this course to steer actually give you a made good course of 130 at 15 knots, you would have to come to 124 and 18.6 knots. 18.6 knots. And that will actually get you your course. And while this is something you can kind of ignore on a paper chart, because it's a lot more abstract and not theoretical, it's just you're running through the motions when you're doing it on a paper chart, it becomes extremely clear on a maneuvering board that to make this vector triangle work, you have to increase speed here for these to actually make sense. If you only stayed at, if you came to 124 and stayed at the same speed, your ER vector would come to right here. And all that would do is you would take your same current vector, your same set and drift, and just shift it that way a little bit. And at that speed, that drift right there, coming to 124 would get you here, which is really close to your original intended track. So you're actually more, let's see, you would be making good 131 instead of 130, which is close enough. Like that's, your course is fine at that point, but you're still going slower than your intended speed of 15 knots. You're under 6, so you're going probably more like, let's see, 6. You're probably more like up nearly 12 knots instead of 15 knots, so you're still not as fast as you intended to. If you want to get your true course and speed of 130 at 15 knots, you would have to raise to 18.6 like we showed here. And I think with that representation there, I think I hope you have a better understanding of what vector triangles are doing. You're manipulating both the angle between these two lines and the length of those lines to adjust what that central line will do. Or in this case, we're manipulating only this one and seeing how it's going to affect this one, because this one will not change. It's the current. We can't control that. It's not a perfect one-to-one analogy for how radar works, because in radar, the R's and the M's are slightly different, but you'll see later on how these two things interplay with one another.